Dear children, we have already discussed that the solids are broadly classified into crystalline solids and amorphous solids. The crystalline solids are those in which the constituent particles are regularly arranged. There is a long range order. But actually it is not the state. Sometimes there are defects or imperfections in the solids. Now what are these defects? When the crystallization takes place, that is, when the crystal formation takes place at a moderate or a fast rate, some defects or irregularities they come in the crystal. These irregularities from the ordered arrangement is known as the defects or the imperfections. Today we will study about these defects, how are they created in the solids, we'll study that. So let's study one by one all the imperfections. The imperfections or the defects in the solids are classified as the point defect and the line defect. Point defect: when the irregularity is around an atom or a molecule, then that is known as a point defect. But when this defect or the irregularity in the arrangement of the constituent particle generates along a row, then that is known as a line defect. We will study in detail about the point defect. The point defects are further classified as the stoichiometric defect, the impurity defect and non-stoichiometric defect. Let's see. Stoichiometric defects: the vacancy and the interstitial defect normal in the non-ionic compounds and in the ionic compound as the Frenkel and the Schottky's defect. First of all, we'll deal with vacancy and interstitial defect. This is the vacancy defect. It decreases the density of a solid. Interstitial defect: here you can see that the extra atoms or the molecules are present at the interstitial sites. They should not be here, but they are here in addition to their normal positions. This is interstitial defect. And since extra constituent particles are present in the interstitial site, it increases the density of the solid. These are normally present in the non-ionic compounds. Now, the stoichiometric defect in the ionic solids. An ionic solid is made up of the cation and the anion. And we have already studied in the class 11th that cations are smaller than anions. Now let's see the Schottky's defect. In the Schottky's defect, the cations and the anions in equal number are missing from the crystal. Now the point is, why in equal number? It is just to maintain the electrical neutrality of the crystal. You can see here a cation should be present, but the cation is not here. It is missing. Similarly, here an anion should be here, but anion is missing. So one cation or a foreign atom or a foreign cation enters the crystal. For example, if in a molten sodium chloride, some strontium chloride is also present during crystallization, then some strontium ions, they enter the sodium chloride crystal. Now we also know that the strontium ion has 2 positive charge, but a sodium ion has +1 charge. When a strontium ion enters a sodium chloride crystal, it brings along with it 2+ charge. To maintain the electrical neutrality of the crystal, now 2 sodium ions will have to move out. Let's see here. Here you can see that a strontium cation enters the crystal lattice. It will replace the 2 sodium ions, but strontium ion will take place the position of only 1 sodium ion, and 1 position of the sodium ion is now vacant. So here you can see there is a cation vacancy. Here should be 1 cation, but it is not there. A cation vacancy is generated due to this impurity. It is again a defect or a imperfection. The non-stoichiometric defect. It is further classified into the metal excess defect and metal deficiency defect. Metal excess can take place due to anion vacancy or due to the presence of extra cations. Now let's see one by one. The alkali metal halides are colored. For example, sodium chloride is yellow in color, potassium chloride is violet, lithium chloride is pink in color. Why these crystals, why these solids are colored? It is due to F center, Farben center. What are these F centers? F centers are defined as when the anion vacancies are occupied by the electron, that point is known as the color point or the F center. These electrons are unpaired, and due to the presence of these unpaired electrons, the crystals are colored. Now, why these anion vacancies are generated? How these electrons enter the crystal, let me explain. For example, if we take a sodium chloride crystal and heat it in the presence of the sodium vapors, these sodium vapors, they get deposited around that sodium chloride crystal. In the presence of these sodium vapors, the chloride ion which is present inside the crystal, it diffuses out. When it diffuses out and comes on the surface, the sodium atom, it loses an electron and changes into sodium ion. Now, the sodium ion and the chloride ion, they unite, combine and form the sodium chloride, and the electron which is lost by the sodium atom, it diffuses in and occupy that site which was left by the chloride ion. Since the chloride ion is a negative ion, that is, it is an anion. Now the site which is left by the anion is occupied by the electron. So we say that the F centers are the anionic vacancies occupied by the electron. These electrons are responsible for the color of the alkali metal halides. Another non-stoichiometric defect is the metal excess due to extra cations. Now, from where these extra cations present? For example, zinc oxide, it turns yellow on heating. Now, how it turns yellow? Actually, what happens when we heat zinc oxide crystal, oxygen is evaporated and the zinc atom loses 2 electron and changes into zinc ion. Now, these Zn2+ ion occupy the interstitial site and the electrons occupy the neighboring interstitial site. Again, these unpaired electrons are responsible for the color of the zinc oxide. Let's see this equation. Zinc oxide is losing 2 electrons and changing into zinc ion, and oxygen is evaporated. These zinc ions occupy the interstitial site and electrons occupy the neighboring interstitial site and responsible for the color. Now, the metal deficiency defect. There are many compounds which are not possible to prepare in the stoichiometry ratio. For example, FeO. In FeO, there are many Fe2 plus ions are missing, and to maintain that positive charge, Fe3 plus ions, they occupy the crystal. Now the charge is maintained, the electrical neutrality is maintained, but the cation is missing. For example, if 3 Fe2 plus are missing, then 2 Fe3 plus ions will maintain the positive charge, but there are 2 Fe cations instead of 3 Fe cations. So, there is the deficiency of the metal cation. This is again a type of defect, a non-stoichiometric defect. So, dear children, we can say that there are imperfections or defects in the crystals. These defects may be due to any reason, due to the missing of the cations or anions, or due to the dislocation of the cation. There may be some vacancy defect or interstitial defect, and these defects changes the density of the crystal. Sometimes it decreases the density or it increases the density, or sometimes there is no effect on the density, as we have seen in the case of the